Now I'm going to talk about dependency parsing as head selection. This article in 2016 by, again, Mirella Lapata, and it's very similar with the article of Christopher Manning in 2017. They are very similar. So I've explained this in lecture 4, in video 4, and so let's talk about this idea. So they created dense model, they call it dense. It produces a distribution over possible heads for each word, just like the idea of Christopher Manning. So using features obtained from a bidirectional LSTM without enforcing structural constraints, so they don't put the constraint that it should be 3. And dense generates at the inference time trees for the overwhelming majority of sentences. Around 85% of them, I think, it creates tree without any problem. But the rest of them can be adjusted by maximum spanning tree algorithm. So dependency parsing paradigms, you can either use graph-based approach, like the MST parser of MacDonald in 25, or the MALT parser of Nivre, which is transition-based. But the graph-based algorithm, it depends on how you want to simplify and how you put your assumptions. If your assumptions are too strong, it is arc factored, the very, very basic model. Then the score of a tree in that model is defined as the sum of the score of all its arcs. But if you're working with higher order dependency parsing, you can use potentials and belief propagation and factor graphs that I like. So although there is nothing inherent in the model to enforce tree structured output, when tested on an English dataset, it is able to generate trees for 95% of the sentences, 87% of which are projective. For example, in Czech language, most of the sentences are non-projective inherently, or rich languages, Japanese, Chinese, Dutch. But English is very simple. Most of them are projective. Everything is simple. Even the Eisner algorithm is enough for the inference because it's projective most of the time. So we have either projective or non-projective. The Edmonds algorithm is the algorithm that we use for maximum spanning tree when we want to work with non-projective trees. And you know that the Eisner, we use it for projective trees only. So dependency parsing, you can think about as head selection. The model takes as input a sentence of length n, for example, 0, 1, 2, 3, 4, 5, 6. We have 6, and then it outputs n head and dependent. Why? Because for each word we only have one parent, but each parent have many children. So that is the idea. And so in word representation, the importance of positional information when a word is repeated. For example, A is repeated. So if you just work on word2vec and say A is this vector, it doesn't have many meaning. It cannot distinguish this A from this A. And that's why positional is important. But in this paper, they only consider, the contextual level, which is with which they use by LSTM, and their final representation is first they augment the word embedding layer with the part of speech tagging, and this is what they mean by embedding. And then they give this X to their LSTM, and it outputs your forward hidden layer and backward hidden layer, because we are working with bidirectional LSTM. And they augmented, this is a very standard technique, to produce the final representation for each word from 0 to n. And in head selection, for example, we say, given a word, what is the probability that omega j is connected to that, is the parent of that, is the head of that. So given omega I as a dependent, what is the probability that omega j is the parent or the head? And D, for modeling this, we use the softmax of G, and G is just this function that is a combination of your I and J. And so we should learn these parameters WA and UA. This is the activation function, and dot product with the VA. And this UA is 2D because D is hidden unit size of your LSTM. And because we have bi-LSTM, so D plus D becomes 2D. And so when we want to train our model by minimizing the negative likelihood of gold standard, we use this minus log likelihood, and N of S is the number of words in the sentence. But we have many sentences. And if we work on that, if we train that, then we are able to find the parameters. But until now, there is no guarantee to form a tree. So it's very greedy. Unlike the Eisner algorithm for projective trees that is bottom up and it's projective, here it can work with for the inference we use that maximum spanning tree, and it is non-greedy. It is greedy, and it can also be used for non-projective methods. So you see, English is easy because 95% of arc predicted are trees, and 87% of them are projective. Whereas Chinese dataset, 87% of them are trees, and only 73% of them are projective. And so what about labeled dataset? We say for labeled dependency parsing, we use the same kind of modeling, that probability that I explained. So it's straightforward if you are familiar with deep learning. So let's work on maximum spanning tree algorithm. You know that we use this for score of each edge, I and J. We use this P of head that we modeled. And because it is known we can model that. Now the problem is reduced to finding the tree with highest score. And for non-projective case, as I said, we use Chiu-Liu at most algorithm. And for projective case, it's very easy if we just use the Eisner algorithm. And the time complexity is order of n cubed. Just like CKY in constituency parsing, the order is n cubed.